past, we've seen how to find the area beneath the curve, or more specifically, the area between the curve and the x-axis. Now remember, when we first developed this idea, we had something like a curve here, let's say something like a square root that, let's give it an endpoint that came over here. If we wanted to find the area from 0 to whatever that is of this curve, remember the way the concept first happened is we put a bunch of rectangles in there. In fact, we put an infinite number of rectangles inside this region. If we added up the area of all those rectangles, it gave us the area between the curve and the x-axis. Now, I've only drawn one rectangle here. This is going to be called a representative rectangle, and it's going to represent, of course, all of them in there. Of course, I'm not going to draw an infinite number of them, so I'm just going to put one in there in this case. Now, the question that we're going to look at today is, what if we took this area and we rotated it around an axis? Let's say we took that and we spun that around the x-axis. Well, what we'd end up with is kind of a shape that looks like, that's horrible. That's absolutely horrible. Something like this, right? We kind of get this solid that looks like, I don't know, a bell kind of shape. So today's question is going to be, what is the volume of that solid, or what is the volume of, in this case, kind of that bell? These are called volumes of revolution because we take a two-dimensional shape, revolve it in a three-dimensional region, and try to find that volume. That's the name. The way that we're going to do this is we're going to follow the path of one single representative rectangle and see what we end up with. So remember, let's go back to our original picture again. My eraser's in the wrong spot. Let's go back to our original picture before we spun this thing around. Looks something like this. This was our region. Now remember, since we're integrating in the x direction here, this rectangle is technically infinitely narrow. And we said that that was a small piece of dx, right? That's an infinitely small piece in the x direction. So if we were just to take this one rectangle here and revolve it around the x-axis, what shape would we get? Well, you'd actually end up with kind of this disc-looking shape. So the question is, what would the volume of one infinitely small disc be? Well, remember, this right here, even though it's not drawn very well, this little distance right there is dx. Well, what we ended up with here, I know it's on its side and infinitely smooth, it's really, that's just a cylinder. Well, what's the area of a cylinder? Well, any regular solid, a regular solid is any solid whose cross-section is exactly the same. See, if I take this and I cut kind of perpendicular to it like this, every cross-section I get would be a circle of the exact same size. So this is called a regular solid. So to find the volume of this, it's always the area times the height. Now the area of the cross-section in this case, the cross-section, well, the area of a cross-section, well, that's just a circle for which is pi r squared, and the height of this is, well, ever how high it is. So there's our volume of our cylinder, if you ever wanted to know where that formula came from. So if we take a look at this as our cylinder, our height here is dx. So here our height is dx. Well, what is the, I'm going to go ahead and do it like this. What is the radius? Well, of course, we got pi here. The radius of this circle, well, it kind of depends on where this representative rectangle is. Would you agree? If the representative rectangle over here would be shorter, over here it would be taller. So the height or radius here, because that would be how far away it is, would be the height of the curve. So in that case, that y value is the function. Now I'm going to call that radius r here, so I'm actually going to call that r eventually. So this is really just pi r squared times height. Pi times the radius squared times the height. Well, that would give us the area of one single strip here, or one of these discs when rotated. So anytime we want to add up an infinite number of things, we need to integrate. So if we add all these up from, I'm just going to say from some a to b, we would integrate from a to b pi f of x squared dx. Now a couple things can happen here. The pi is a constant, so we can pull that out. And I'm going to call f of x our radius, so r. This is generally called the disk method for finding a volume because once we rotate one of those representative rectangles, we get a disk. This is actually a special case of another shape. That's why I generally don't want you to kind of think about this. By the way, this is our, I think you use disk. It's called the disk method. I don't want you to memorize this one because this is, like I said, a very special case of another method. Let's take a look if our original picture had changed a little bit. What if our original picture had been something like, that's our region, and we want to rotate that around the x-axis? Well, when you put your representative rectangle somewhere in there, now it has kind of the top and the bottom. And if you think about spinning that thing around the x-axis, what shape would we get? Get this out here. Well, kind of the outside's still going to give you this disc shape, but you're going to have this also a hole in the middle. So you're also going to have this kind of happening there. Now remember, our axis is running through this, so it goes that way and then out that side. So my question is, what's the volume of this? By the way, we generally call this a washer. You know, like you've seen like nuts and bolts and washers. It's kind of a washer. So what would the volume of that be? Well, it's just the volume of two cylinders. The big cylinder minus the little cylinder that came out of the middle. So if we call the distance here, and I'll give exact definitions of that for a second, big R, so that would be the distance from the axis of rotation out there, that would be big R. And this little distance right there, little r, that would be, say, from right there to right there would be little r. Well, the volume of the big cylinder, the big part, would be, let's just go from A to B, pi big R squared dx. But then we'd have to take away the inside from A to B, pi little r squared dx, which we can combine into just one integral because they're both from A to B, and they both have this constant pi, so I could write this as A to B, big R squared minus little r squared dx. This is called the washer method. And I'm going to give you definitions for big R and little r here just in a second. Now notice, this reduces to the, the disk method if little r is 0. See, in this case, we do have a distance from the axis of rotation to there, but watch, I'm going to change my picture a little bit. If this hadn't been there, this representative rectangle would have gone all the way down to the axis. Now that's still big R, but little r, since it's touching the axis of rotation, there's no distance there. So little r is 0, and notice that's the exact formula we had for our disk method. So here's two definitions that we need. What is that big R? That's the longest radius. Big R is the distance from the axis of rotation to the outside edge of the representative rectangle. Okay, so big R is the distance from the axis of rotation to the outside edge of the representative rectangle. Little r is the distance, blah, 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 to the, why did I spell inside wrong? Inside edge of the representative rectangle. All right, so when we are doing these rotations, we need to know what axis we're rotating around and the distance from that axis to the farthest edge and the distance from the axis to the inside edge. Now, depending on what we're rotating around is the direction that we're going to put our representative rectangles. So one more sentence here, and we're going to try a couple of examples. All right, for the washer method, as you see here, our axis of rotation was the x-axis, and our representative rectangle ended up being perpendicular to it. We're going to use another method a little bit later on to where it's not perpendicular, so that's important for this method. All right, let's try a real quick example, a couple of quick examples of this. Let's actually do the one we started with. Let's say find the volume created by revolving the region bounded by, let's do y equals the square root of x, y equals 0, and x equals 4. And we're going to do several problems. Let's do about the x-axis first. It's kind of going to be the easiest. So we're going to go about a couple of different axes to see how this works. All right, so I highly suggest you follow the steps that I'm going to do here. If not, you're going to get very confused. Very few people can just look at this and write down the integral. It's visually difficult to do. Always sketch the region first. Now, it doesn't have to be an exact sketch, just a very quick sketch. I know about what the square root of x looks like, something like that. Y equals 0 is the x-axis, x equals 4 is a vertical line, and they intersect about right there. So I know that this is x equals 4, I know that that's at y equals 2. I'm just going to put 4 there. All right. Once you've sketched the region, next thing you need to do is put your axis of rotation. I do that by the little spinning arrow thing I drew. Since we're going about the x-axis, draw yourself a little spinning arrow. Now, since you know the axis of rotation is the x-axis, we know that the representative rectangle is perpendicular. So somewhere in the region that you just draw, that's this triangular-ish region here, I'm going to put a rectangle perpendicular. All right, now, this seems trivial, but it defines the entire problem. As soon as you put that representative rectangle in there, would you all agree when I pack them in there, it's going to squeeze it in the x direction, which means that's a little piece of dx. That dx defines the entire problem that we're getting ready to do. All right, so for problem 1, or setup 1, we know from our formula, and I'm going to actually, let me just stick it over here. This is pi times the integral from a to b, big R squared minus little r squared dx. That's our washer method. And generally, you're going to always want to use that. Don't think about it as the disk method. Okay, so for this problem, I can already do this. I can go pi integral dx. Now, the reason I need the dx there, because that now tells me everything inside of here has to have x's in it, and these bounds have to be what x runs from. Okay, so looking at this picture, let me grab this marker. Looking at this picture, we need to figure out what big R is and little r is. Big R is the distance from the axis of rotation up to the top edge. Now, since we're measuring up and down, these are y values. So the axis of rotation is y equals 0, and the top edge is touching y is equal to the square root of x. So how far is it from here to here? Well, it's whatever that y value is on that curve. So big R is just the curve itself. So that's going to be, I'm going to move that dx over a little bit. That's going to be the square root of x squared. Our little r is the distance from the axis of rotation to the inside edge. Well, since the inside edge is touching the axis of rotation, that is 0. All right, for this region, what does x run from? Because that's our dx told us that. X is going to go from 0 to 4. All right, so for most of these today, I'm just going to set them up for time's sake, because most of these integrals are going to be trivial, basically integrals. I mean, that's just the integral from x from 0 to 4. I'm guessing y'all can do that. So, because I want to get a lot more examples up of how to set this up. All right, what if we were taking this and we were going about the y-axis? All right, now, if I were you, I would sketch this region again, but just for space on my board, I can't really do that. So I'm gonna erase everything that I have here, and I'm gonna do my picture again. Should probably just sketch this completely new. All right, this time I'm going around the y-axis, which means my representative rectangles now go in this direction here. Since it's going in this direction, you kind of think about we're piling up an infinite number of rectangles this way, which means it gets squeezed in the dy direction. Now we can already set up the outline for our whole problem. This is going to be pi times the integral, big R squared minus little r squared dy. So the dy tells us these have to be stuff with y's in it, and this has to be what y runs from. Okay, so from this picture, big R is the distance from the axis of rotation. Ooh, that's a horrible bracket. To the outside edge. Little r is the distance from the axis of rotation to the inside edge. Now, I missed that a little bit, but the inside edge. Now, since we're measuring horizontally, we're talking about x's, right? So this goes from, how far is it from x equals 0 over to x equals 4? Well, that distance right there is constant, right? It always is a distance of 4. So big R is 4. Little r is the distance from the axis of rotation over here. Well, that's from the axis of rotation to the curve itself. Now remember, this curve is y is equal to the square root of x. But here we need to know what x equals because we're measuring in the x direction. So from this, what does x equal? Well, x is equal to y squared. So the distance from here would just be y squared. Okay, so what does y run from in this bounded region? Y runs from 0 to 2. There we go. All right, let's try another one. Let's go about something completely different. What if I said, let's go about the line x equals 5. Okay, again, I would highly suggest you drawing a brand new picture. I am, but I gotta get rid of the old one. So, drawing the exact same picture. That's 4, 2. Now in this case, we have the line, I'm gonna right here, this is x is equal to 5. That's my axis of rotation. So if that's my axis of rotation, my representative rectangle goes perpendicular to that. So that is my representative rectangle, which in this case means I have a small piece of dy. So I can set up the framework for my problem already. Pi times the integral, big R squared minus little r squared dy. It means everything has to be in terms of y. So big R is the distance from the axis of rotation to the outside edge. So how far is it from x equals 5 to this? Well, this confuses some people, but if you think about it like this, if I just gave you a number line, and I said over here 7, how far is it to 3? How did you do that? What's that distance there? It's that minus that, right? Well, what if I don't know what that distance is right there? What if I just know that's some x value? Well, that distance would be 7 minus whatever that x value is. Same thing happens here. This distance is going to be, well, 5 minus whatever that x value is. And we just saw a second ago, x is equal to y squared. So our big R here is going to be 5 minus y squared. Little r is the distance from the axis of rotation to the inside edge. So that's our little r right there. Well, that's always a constant, right? It's that x value minus that x value. So 5 minus 4 would just be 1. All right, let's do one more, and I'll bring it up here. All right, do me a favor. How about you pause the video for a second? Set up your picture and see if you can set up this region. All right, let's see if you're back. So again, I gotta change my picture up just a bit here. You know, I'll just sketch it right here. It's already over here. Looks like this. That's 5, that's 2. We're going about the line y equals 4, that's up here. So that's our axis of rotation. Our representative rectangle is perpendicular to that, and you can see now that we're gonna have a little piece of dx, because that's which way it would be squished. So the outline for our problem, pi big R squared minus little r squared dx. That tells me everything now has to be, I'm sorry, this is a 4. That means everything has to be in terms of x. All right, big R is the distance from the axis of rotation down. Now remember, these are y values since we're measuring up and down. So how far is it from y equals 4 to y equals 0? Because that always stays at y equals 0. Well, that's always 4. That's our big R. Little r is the distance from the axis of rotation to whatever that y value is. Well, on this curve, we know y is equal to the square root of x. So on that curve, it's going to be 4 minus the square root of x. All right, so if you have an off-axis, something that's not the x-axis or the y-axis, generally you're going to have this type of subtraction thing coming in here, so keep an eye out for that. All right, let's try another region. All right, we're going to just do a couple of these. Let's do, same idea. This is the region bound. Let's do y is equal to x squared plus 1, y equals 0, x equals 0, and let's do x is equal to 2. But again, we're just going to do 2 of these. Let's go about the x-axis first. All right, to sketch our region, this is a parabola shifted up 1, so it looks something like that. X equals 0, y equals 0 are our axes, and x equals 2 is somewhere over here. Let's call that 2. So this kind of boxy region right here is what we're looking at. Something like that. All right, so let's do a couple y values. We know that that's at 1 because it's our parabola shifted 1 point. If we plug in 2, that would be up there at 5. All right, we were told we want to go about the x-axis here, so there's our rotation. So since we're going about the x-axis, that is our representative rectangle. All right, so with that, we should be able to set up our problem already. Since we're going about the x-axis, that means we're going to have a little piece of dx here. So this is going to be pi times the integral big R squared minus little r squared dx. Because everything needs to be in terms of x's. Big R, the distance from the axis of rotation out. Well, notice the top edge is always touching the parabola, and that's, since we're going up and down, that's a y value. And on the parabola, we know y is equal to x squared plus 1. So this would be x squared plus 1. Little r is the distance from the axis of rotation to the inside. That's little r there. Well, since it's touching the axis of rotation the entire time, that would just be 0. All right, so that was pretty easy to set up. Let's take a look at if we have to go about the y-axis. So same basic picture. I'm just going to change my representative rectangle. So since we're going about the y-axis, there's my axis of rotation, we would draw a representative rectangle kind of like this. Since it's squeezed this way, we get a little piece of dy, which means, again, oh, I forgot my x went from 0 to 2. Fix that, right? And the last one, x goes from 0 to 2. All right, so we can set up our bounds. We go 0, big R squared minus little r squared dy. Okay, what is big R? Well, big R is the distance from the outside, or from the axis of rotation to the outside. And here, since we're going horizontally, that's just an x, so the distance from 0 to 2 would be 2. Little r, since little r is touching the axis of rotation, little r would be 0. And that's the answer that I get most time on a problem like this. Here's what's wrong. what if I had drawn my representative rectangle in this region up here? Notice for the top region, let me go ahead and put that little mark there. For the top region, big R would be the same, but little r is different. So here's the idea. You got to mentally picture, if you move your representative rectangle throughout the entire region, if either side changes what it's touching, you need another integral, right? So we're able to do big R and little r as 2 and 0, but only in the region from y goes from 0 to 1. Then, so plus, I got to add another one. All right, so in this top region, big R stays the same, right? Because big R is still touching the right side of that curve. That's still 2. But little r is this x distance here. So what does x equal? So we need to take this and figure out what x is equal to. So if y is equal to x squared plus 1, y minus 1 is equal to x squared. So x is equal to plus or minus square root of y minus 1. Now we know it's the positive because we know we're on the positive x side here. So this curve here is x is equal to the square root of y minus 1. So little r is that distance there, square root of. So you got to be careful. If your representative rectangle changes what it's touching, then you need a separate integral for that region. Now, what does that run from? Well, that y value starts at 1 and goes up to 5. And if it changed again, you would need a third. And if it changed again, you would need a fourth. But for most of the time, what we see, it generally only changes once. All right, so we'll do one more quick example. I'm actually going to set it up and let you guys try this. So, saying find the volume of the region bounded by, excuse me. Let's do y is equal to x squared, y is equal to x, and okay, so do me a favor, pause the video and see if you can set up these 4 regions. All right, so video time means you're done already. So let's go ahead and give it a shot. The very first thing we want to do is sketch this region. Well, I know what both of these look like. That's a parabola and that's just a line with a slope of 1. But if this is a bounded region, I need to know where they intersect at. Kind of like before when we were doing area between two curves. Well, that's easy to see. That's when x is equal to 0 and x is equal to 1. So I know when I sketch this region, I know they're going to intersect there because they're both 0 there. So I've got a parabola over here to 1 and a line coming back. So that's what our region should look like, hopefully. So from that one picture, let's see if we can set up all of these. The first one, about the x-axis. About the x-axis would be rotating this way. Our representative rectangle is perpendicular, means I have a little piece of dx. So I'm going to go ahead and set up the framing work for this, dx. Big R. Big R is the distance from the axis of rotation to the outside edge. Now remember, that's a y distance. So what does y equal at the top? That equals y is equal to x. And on the bottom, of course, that's x squared. So big R would be x. Little r, the distance from the axis of rotation to the inside edge of that represented rectangle, would be x squared. All right, that's the first one. Oh, what does x run from? Sorry, x goes from 0 to 1. Forgetting those bounds today. Don't forget your bounds. For the second one, what did I say? About the y-axis. So the only thing that's really going to change here is now my representative rectangle switches. So now it's got to be perpendicular to the y-axis. So now we're going around this way. Means I have a little piece of dy. So this can be pi times the integral big R squared minus little r squared dy. Big R is the distance from the axis of rotation over to the curve. Now that's the curve y is equal to x squared. Since we're measuring horizontally, we need to know what x is equal to. So that means x is equal to the plus or minus square root of y. Since we're on the positive side of the x's, we know x is just the square root of y. Now for our other curve, that's really easy. That's just y is equal to x, so x is equal to y. So big R is the distance from the axis of rotation over there. That's just that x value. So that would be the square root of y. Little r is the distance from the axis of rotation to the inside edge. Again, it's just that x value there, and of course the x value there is equal to y. All right, since we're going in the y direction, what y values cover that region? Y goes from 0 to 1. All right, next one was about the line x equals 2. Let's get that out of here. Actually, just kind of sketch this again, clean it up a little bit. About x equals 2, there's our vertical line. I just said 2. X equals 2. Our axis of rotation goes that way. Our representative rectangle is perpendicular to that. That means I have a little piece of dy. So I can set my framework up. Okay, so big R is the distance from the axis of rotation to the outside edge. So it's that distance there. Well, again, since we're measuring from the off axis, it's going to be this x value minus this x value. Remember, the distance from here to here, that is x is equal to y, and the distance from there to there is x is equal to the square root of y. So, how far is it? Well, the distance from the axis of rotation to the outside edge is going to be 2 minus that, so this is going to be 2 minus y. And the distance from the axis of rotation to the inside edge is going to be, well, again, 2 minus the curve, so 2 minus the square root of y. All right, little bit more tricky on that one. So let's try our last one here. Oh, by the way, y runs from 0 to 1 again. Same region. All right, again, I need to clean up my picture. So our last one. All right, where are we at? What do we go about? Y equals 3. So way up here at y is equal to 3, that's our axis of rotation, which means that's our representative rectangle, which means I have a little piece of dx. So we can set up the structure of our problem. Big R squared, little r squared dx. Now since we're measuring this way, big R is going to be that distance there, little r is that distance there. Well, since we're measuring vertically, we need to know what y is equal to. On the bottom curve, we know y is equal to x squared. On the top curve, we know y is equal to x. Now, so how far is it from here to the outside edge? Well, from here to here, all the way down is 3, but we got to back up that little bit there, whatever that y value is. So that's going to be 3 minus x squared. So again, how far is it to the inside edge? The entire distance is 3, but we got to back up whatever y value that is. So it's 3 minus x. Now, of course, the same region, so x does cover from 0 to 1 here. So there's our setup. All right, now we didn't work out any of these integrals, but for your homework, you're going to need to at least practice your basic integration skills. As you see, we didn't end up with any that were very complicated, but the arithmetic for these does get messy along the way, so deal with it.